Last week, we spent some time solving for zeros, remember? And solving for zeros meant where we're finding where this parabola hits the x-axis. And we had two solutions, or we had one solution if we're sitting on it. And then we really didn't talk about this. We had a couple in our homework that were no solution. But the idea here is that you can have parabolas that never cross the x-axis. We can also have parabolas. When I make you guys your homework problems, I try and give these. We did have some estimating ones where we had decimals, but in general, I try to do whole numbers. And we're going to find out how to actually calculate those crazy decimal ones, and it is quite crazy. But today we're going to start getting the tools to talk about no real solutions, because when we use this word real solutions, math says by definition that there has to be two solutions for all of these quadratics, meaning that even though this is only one solution, technically it's two identical solutions when we factor. And so their way around that is that they say we can have complex solutions. So if you remember, when you type in like the square root of a negative number, it gives you an error. Okay, we're going to move away from that for a while. Now we're going to say that thing does exist. And what that is we're going to call that the imaginary unit I, and it's the principal square root of -1. So this is a funny concept, and I can't remember which mathematician had the pleasure of giving this to us. But basically, by definition, what they say is that the square root of -1 is I. We have this cool pattern that happens, and I say cool somewhat in quotations. So I squared, if you imagine I is the square root of -1, I squared is the square root of -1 times the square root of -1. Does anyone remember what happens when you multiply two identical square roots? They combine. So like, what's the square root of 2 times the square root of 2? It is the square root of 4, which is what? 2. So you guys remember that rule? Like, if you don't write this down, but like if you do the square root of 3 times the square root of 3, it's 3. If you did the square root of 100 times the square root of 100, it's 100. It's just by definition, like how these square roots work. Anytime you have a pair, if you multiply them together, you just get that inside part. So the square root of -1 times the square root of -1 is just -1. So I squared is -1. I cubed, if you think of this as like the square root of -1 times the square root of -1 times the square root of -1. Well, we just said that 2 of these, right, is just -1 times the square root of -1. But the square root of -1 is I, so this is the same as -I. And then I to the 4th, it's really weird, square root of -1 times the square root of -1 times the square root of -1 times the square root of -1. So if two square roots of -1 are just -1, this is the same as saying, okay, -1 times -1. What's -1 times -1? +1. So by definition, I is the square root of -1. I squared is -1. I cubed is -I. And then I to the 4th is 1. So what happens is after I to the 4th, the pattern starts repeating. So I to the 5th is really the same as I, because it's like taking these 4 square roots of -1 and multiplying them by one more square root of -1, which is just I. We'll use that a little bit. That's just kind of a fun fact of the universe. And if you see it on your SAT, I want you to be able to roll with it. So these imaginary numbers, they come in a certain like form. And today we're going to talk about just a pure imaginary number. Pure imaginary number. I ran out of room. Let's put the little hashtag for number. You guys know that means number. Is of the form bi, meaning there's a number times I, where b is a real number and I is equal to the square root of -1. So there's a difference between like complex numbers and just pure imaginary numbers. Pure imaginary numbers just have the imaginary part. Complex numbers will have a real part plus or minus the imaginary part. And we'll talk about that later. So numbers of the form 6i, -2i, and I times the square root of 3 are called pure imaginary numbers. Just so you guys know, like when you generally write square roots, you know how like you would never put x2, you'd always put 2x. You guys know what I'm talking about? So there is like kind of a conventional order here. The conventional order is that you would do like a number times the imaginary part times the root part. Okay, so number, imaginary part, root part. If you didn't have the number part, it would just be the imaginary part times the root. If you didn't have the root, it would just be the number times the imaginary part. And then obviously if you didn't have the imaginary part, it would just be the number times the root. I won't mark you wrong for doing that, but Go Formative will, because I can't predict all the ways you guys would enter those answers. So that's just some stuff about imaginary numbers. Let's get to using them. Okay, so square roots of negative numbers. If you were to take your calculator and type in the square root of negative 294, your calculator would very rightly say error. Because by definition, a square root is saying what two numbers multiplied by themselves is this inside number. And this is saying that it's possible to have two identical numbers multiplied to a negative number, and we know that that's not true. Again, though, our math is like, okay, well, hold on. We need a solution for this. So what they want us to do instead is to split this up. Think of this as -1 times positive 294. But what did we say the square root of -1 was? What is the square root of -1? It's an I. So when you see a negative, I want you guys just to pull out an I, and then you'll have this whole number here. We're not done. I still have to clean up that 294. But basically, if you see a negative, pull the I out. You should never have an I under the square root. It's always outside of the square root, because that's what it means by definition. All right, now let's talk about simplifying these square roots. So I like to use like the list of perfect squares. So like your list of perfect squares is 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. That's your first 12 perfect squares. Does anybody have those memorized in here? Ish, kind of. Yeah. I will give you some, but like it kind of ends up happening anyways. I'll say 13 and 14 have a cool pattern. 13, I memorized this when I was at Powers. I used to look out my window at I-69, and 13 squared is 169. And then 14 squared is if you just switch the 9 and the 6, it's 196. And then 15 squared, does anyone remember 15 squared? 225. And then beyond that, honestly, I don't even have it memorized.
I just think of adding it together, and it'd be like 2 2s and then the 5.
Yeah, exactly. You know, it has to end in a 5.
Saying it out loud, it doesn't make sense, but in my head,
Well, yeah, the same thing with the 169. Like 13 has nothing to do with I-69, but it's
stuff. The amount it goes up adds up by 2 every time. First 4 to 9 goes up by 5, 9 to 16 goes up by 7, 16 to 25 goes up by 9.
Oh, look at you.
Yeah.
That's a cool pattern I never noticed. So there's ways, I don't need you to memorize these, but there are ways to do it. So if you have these memorized, it makes this pretty easy. I say easy in quotations. So what I like to do is I like to just go through my list. 294 divided by 4. I have a decimal. Those are not divisible. 294 divided by 9. I have a decimal, not divisible. 294 divided by 16. I have a decimal, not divisible. I know 294 is not divisible by 25, but just if you like the routine. 294 divided by 36. 294 divided by 49. There it is. So as soon as you get that whole number, you can break this into 49 and 6. And then the power of doing that is I know that there's no pairs in 6. There's no like, I know 3 plus 3 is 6, but we're thinking multiplication. 2 times 3, that's not a pair. However, in 49, 7 times 7, that's a pair. And do you guys remember the idea that you have to have a buddy to break out of jail? Yeah. One guy dies, because math is dark. One guy dies so the other can escape. So then you'd have 7i times the square root of 6. That is a fully simplified square root with a complex part. Yes.
So it's not them dying. I was a little bit like, you know, they have like the two kids stacked in a trench coat with like the thing over.
Oh, that's a cuter way of thinking. Yeah, that's a cuter way of thinking of it. Instead of them dying. Yes. I have very dark examples. The whole division divorce thing.
Yeah.
What is it, called when they like a 2 divided by here, but you have the ones that can't be like squared, and then the other ones that can't be.
Where they're a perfect square.
That are perfect squares, what are those called?
When they're not perfect. I don't know,
Like-
they're not.
Like, you know, 2, 3, stuff like that, that can't be like.
Oh, prime numbers. Prime numbers, yes. So you could think of, I underlined the 6, but 6 is 2 and 3, and those are 2 primes, so you know they're done.
Our teacher, she gave us a chart, and it was the prime numbers and then the perfect square.
Yeah.
I should think of the name of the other perfect.
Yeah, prime numbers, and that helps too. Yeah, if you're good with your primes, that does help. All right, so let's look at square root of negative 45. So what's going to be your first step here? You see the negative, what should you do first? Just pull it out. Make this I times the square root of 45. Without even running through my list, does anyone see which perfect square is going to divide 45? 9. You should be pretty quick. I mean, this is not the first time you've seen this. If you're not quick, that's fine. So, Erica, to your point, 5 is prime. 2 is actually also prime. It's the only even number that's prime.
Saying like 2.
You have your pair, and as Emily said, maybe they don't die, but they stack on top of each other, and 1 3 is going to come out. So it'd be 3i times the square root of 5, the guy that's left that didn't have a buddy to hide under the trench coat with him. All right, just as a reminder, what about this? Just looking at it. Can anyone tell me the answer? 12. So don't forget to look out for those perfect squares. If it's already in your list, it is itself a perfect square. It already breaks into a pair. So you know that a 12 is going to come out, and I will also come out. So we just have 12i, and do we have a square root left?
No.
No. I have a lot of students that really struggle with that when there's nothing left. They want to have something, but there's nobody left in jail. I mean, I guess there's a 1 left, but we don't care about 1. Okay, so that part's pretty straightforward. I'm going to do a few more just as a reminder of how multiplication works. So example 2, we have negative 2 times 8, square root of negative 2 times the square root of 8. And we kind of already discussed this when I asked you what, the square root of negative 1 times the square root of negative 1 is. You can combine these under 1 square root, and I'm going to write an extra step here just for our notes. You can combine it like that. And then you go ahead and just multiply them. So you have negative 16, which is convenient because, again, 16 is a perfect square. It's 4 and 4. And I have this imaginary part that's going to come out. So I end up with just 4i. It's going to be really tempting to put negative 4i or negative 4 or something like that. Make sure you just put your I. Same thing when you have like on the outsides and on the insides here. So you can multiply outside to outside and the inside to the inside. So it would be 6 times the square root of negative, would be 200. You can take a step and just boot out that I, 6i times the square root of positive 200. And then you should be pretty quick with these. I see that the biggest one that's going to break down 200 is going to be 102. You're not as quick with those. It's fine. You can run through the list. But that's 10 and 10. 25 and 4 would have worked as well. Yep. Well, it'd be 25 and 8, right? And so then you still have a perfect square hiding in there.
I meant for the 100. Actually, it could be 25 and 4 instead.
You could, but then if you do the 10 and 10, you already have a pair there. So then the 10 comes out, but you already have a 6 out there. So it's 6 times 10i times the square root of 2. So you end up with 60i times the square root of 2. So the biggest danger, honestly, with these is there's a lot of little moving parts, and you might lose something. So just watch yourself on that. There is a way to check your answer, sort of. If you want to check your answer, you can just disregard the negative, and you can do 2 times the square root of 10 times 3 times the square root of 20, and you'll get this ugly decimal. And then just take this number minus the I, do 60 times the square root of 2. And if you have the correct answer, it should be the same matching ugly decimal. So if you have time and you want to check your answers, that's how you can do it. And just disregard the negative in the I part because your calculator does not know what to do with that. All right, last example, just because, again, with that SAT thing and showing you how to manipulate the I's. This square is only on the 6I part. So this is the same as 2I times, if you distribute that square in, this becomes 6 squared I squared. So then we have 2I times 36 I squared. And there's a couple ways to do this. First of all, let's take care of the numbers. What's 2 times 36? 72. And then I times I squared. Two ways to do this. You can either call that I to what power? I to the third. Or you can remember I squared is what? I cubed is negative I, or I squared is negative 1. Either way, you can break this up into a negative 72I. Okay, those take a while, and I wouldn't stress that. It's not going to be on your quiz, but again, I'm showing you this. It's on your homework today because I want you guys, if this is on the SAT, it's this cool idea that you can take multiples of 4 and break them into what these I's should be. And it's like a fun exercise to think about because, again, the other way you could have thought of this was 72I squared times I. And if you can remember, I squared is negative 1. That's where that negative 72 comes from. Okay. Again, not on the quiz, but it's like a fun little exercise for your brain. It's kind of like modular arithmetic, which is thinking in remainders. It's fun. Okay.